Okay, good afternoon all. So in the last class, we looked at the difference between derivability, provability or validity and truth. And as I mentioned, derivability or provability, it is purely a logical concept, whereas truth has something to do with reality. Okay, so you have some reality out there. It can be a particular universe, this universe, or other universe. You can imagine this entire classroom as one universe, and one can try to model only this universe using a formal system. So we can define, uh, we can choose what our reality is, and we can try to build a formal system which tries to capture this reality. Okay, so truth has something to do with reality, whereas provability or derivability is purely a logical concept. Okay, like I said, both are independent axes. You can think this is derivability, this is truth, and the reverse is underivable, and the reverse x-axis is like false. Okay, so you will have four planes of all four possibilities. Okay, and then I also mentioned that these are like the different possible worlds. So if you take two premises, you will get four possible worlds, maximum four. You can't think of another possible world. Okay, so in each world or in each universe, some statements are true, some statements are false, but the logic is same. Given these two premises, if you follow the logical rules, you will get the same conclusion. Okay, so the derivability is same across worlds, whereas the truth value will change according to the word. All right, and all this I mentioned so that we can discuss the formal features of a formal system. So the first feature is soundness. Okay, so using these concepts, derivability and truth, we will define some of these formal features. So what is soundness? If all the statements that are derivable within a formal system F are true in the universe U corresponding to the system F, then F is said to be sound. So like I said, your F may have some axioms and some rules. You can derive some statements from these axioms. Okay, now all the derivable statements, if you take that entire set, if there is not a single false statement, then that system is said to be sound. If among the derivable statements, if there is at least one false statement, then the system is said to be unsound. Okay, so let me give you an example. Suppose let's take these four statements. Say area of a circle is pi r square, perimeter of a circle is 2 pi r, area of a triangle is half bh, and some statement like 2 plus 3 equal to 5. Okay, now let's assume these are the only derivable statements in F. Okay, if only, yeah, any doubt? If only these statements are derivable in F, then F is said to be sound because they are all true statements in the universe of mathematics. Now, suppose I am able to derive the statement like this: 2 plus 3 equal to 7. Then my system is no longer, okay, because in the universe of mathematics, this statement is false. If this can also be derived in F, then F is said to be unsound because it's a false statement in the universe of mathematics. So here the idea is I'm trying to build a formal system which tries to capture the universe of mathematics. Okay. So here the understanding is that numbers have their own existence. Okay. Numbers, you may have some symbols, some representation to these numbers, but numbers behave in a particular way. 2 plus 3 will always be 5. Whatever labels you can, you can call in your, you can call 2 as 10 as 4. But this so-called 10 and 4, whenever you add them, will always give whatever number in your system. It may be 12. It doesn't matter. Okay. So the point is, when you add 2 and 3, 5, add 2 and 3, 4, whatever labels you give them, it doesn't matter. Okay. Arabic numerals, you can represent them as Roman numerals, whatever numerals you represent them, there is some number called 2, some number called 3, 4, 5, and so on. Okay, they behave in some way. So that behavior you're trying to capture. Okay, so if 2 plus 3 equal to 5, then 2 plus 3 can't be 7. All right. So if you are proving a false statement also in your system, then your system is not sound. Fine. Okay, you will get more clarity as we proceed. I'll spend sufficient time on this. I'll give more examples, so don't worry. So another way of understanding soundness is like in set notation. So if I have a set of all derivable statements, if this set is a subset of all the true statements, that means you may leave out some true statements, but whatever you are deriving, all of them have to be true. Okay, then the system is said to be sound. Okay, so the derivable set is a subset or equal to the true statement set. Okay, where DS is the set of all derivable statements within the formal system F. Okay, and TS is the set of all true statements in the universe U which F is trying to model. Okay. This is clear. We will come back to it. Any doubts? Yeah.
So when you said derivable or derive, what exactly do you mean?
Like example, all men are mortal. Socrates is a man. Hence, Socrates is mortal. This is derivable. So Socrates is mortal is a derivable statement in that system. But Socrates is immortal is not derivable given these premises. Okay. So some statements are derivable. Some statements are not derivable.
Okay. So can we say a formal system is a set of premises?
Plus rules. Formal system is a set of premises plus rules, so that you can apply these rules on these premises, which we call as axioms, to derive new statements. Yeah. Yes.
How do you know that the state is more false? Because in the formal system, we don't have any reality. So we don't know that the state is more false.
That's why within formal system, there is no question of truth or falsity. When you try to assign a truth value to a statement, you assume that each word refers to some object out there. Like I said, all men are mortal. I am using the words men, mortality, Socrates, etc., assuming that whatever is my understanding of men, mortality, Socrates in this world, I am using them in that sense. But I may choose to build a formal system where I use these words, but in an entirely different sense. In this world, men means maybe some dog in real world. In formal system, men means in real world dog. I can choose to use them like that, but I'm not doing that. I am trying to use the words which I use in reality as it is in the formal system. Now I can make a statement in my formal system. All men are non-living beings. I just make such a statement. In my formal system, this can be a premise, this can be an axiom. But when I try to look at reality, that's not the case. If I am using these words in the same sense, men, as I am using in the real world, non-living beings, as I am using in the real world, if these words also carry the same meaning, then this is a false statement because it is not mapping to reality. That's all.
Why do we use formal system when we are ultimately dealing with reality only? Why do we create this formal system? We separate these formal systems from reality so that our logic works there. But at the end, we eventually come back to reality to check the soundness of the system or other features. So they are not completely differentiable from the reality system.
No, they are. They are absolutely differentiable from reality if you want to. If you want to connect with reality, you can. If you don't want to connect with reality, you need not. So you will understand when we look at other features, completeness, decidability, consistency, you will understand that a formal system can stand on its own. But if you want to use a formal system to understand reality better, then you need to map to reality, right? I can build a formal system which is completely cut off from reality. See, something like you can create a new language or new rules or new, it's like a game. Imagine you are creating a game. Now, some games may represent reality. Like if you have chess, the words which you use and the kind of connotations which you use, they have some relation to reality. Okay, you are trying to fight with the opponent. It's like a war. You have some names like horse, elephant, king, queen, all these things. You are mapping to reality, but I need not. I can use different words. I can have different rules. I can make my own game. It's up to me. But usually formal systems are built to understand reality better. Because natural languages, it's like any programming language. Why is programming language built? You have natural language. Why can't you speak to a computer in that sense? Computer won't understand. You have to create a new language so that the flaws of natural language can be done away with. Like natural language has ambiguity. There is a polysemy problem. There is synonymy problem. Two or more words may mean the same thing, or one word may have more than one meaning. And you can write poetry in natural language. You can use metaphors in natural language. Natural language, you can. It is very rich. That richness is also bringing in a lot of ambiguity with it. So you want to do away with that ambiguity. You want to create a language which may be limited, but which is unambiguous. So formal systems are built with that idea. Okay.
Does that mean doesn't have these features can be formal?
System which doesn't have these features can be formal. I don't know. One should imagine like what system can be there without this. Like reality, you can think of as an open system which doesn't have these features, but reality is not formal. It should have some of these features. It should basically, formal system means you should define that system. What are the axioms? What are the rules? That's it. Whatever else you want to do, you play with these rules, with these axioms. Whatever you get, that is, you may not know what new statements it may derive. Because if your corpus of axioms is very big, and if you can combine them in 1,000 different ways, then you may look at an output statement which you did not imagine. But it's not that this output statement is not present in the premises. It's just that our mind is limited, that it could not combine all possible combinations and permutations that this output statement is possible. That's all. It is like Lego bricks. Lego bricks are there. You combine them in any way you want. That's a game. There are rules. It allows you only in so many possible ways. Formal system is like that. Sorry? It is trying to model, like I said, if I want to model, say, this room, suppose this room is my reality. Okay. Now I define what are the entities in this room, relations between them. Corresponding to them, I create some axioms and some symbols. Okay. Now, the relations which I have will also be corresponding to the entities in this room. I want, now in this room, what are there? People, students are there, boys, girls, chairs, table, projector, these things are there. I won't need to think of objects like elephants, horses, donkeys, monkeys, or stars. None of those things are necessary for my formal system. So within my formal system, since I am trying to model this room, I will limit my objects as well as relations to this room. So this is my universe. I may choose to build a formal system independent of this room. But right now, if I want to model this room, then my formal system will have some connection. The words and the operations in my formal system will be related to the entities and relations in this room. So this room is my reality, and the symbols which I use are part of my formal system. It's like language. Formal system is nothing but language. Language is always not a reality in itself, right? Language is a representation of reality. Similarly, a formal system is a representation of some reality. Which example? Set of all true statements in the universe, U, which F is trying to model. Okay. So for instance, I can say there are some 300 chairs in this room. So I have a word called chair. I have a word called room. I have a word called in. I have a word called are. All these words are there. So each word should correspond to an object. There are objects, chairs, and the word chair which I am using is corresponding to that object. The word room which I am using is corresponding to this room. Okay, that is one thing. Another thing, I can have another statement. All the chairs in this room are green. Okay, suppose I can have another statement. Some chairs are green, some chairs are red. I may have such a statement, but that will be a false statement with respect to this room. And I can say, in each chair there is one student, which means, and in no chair there is more than one student or less than one student. From this I can conclude that there are as many chairs as there are students. So this last thing which I am concluding is a logical conclusion. If in each chair there is exactly one student, no more, no less, then the conclusion is there are as many chairs in this room as there are students. This is one way of counting also, right? Suppose if you have two sets, how do you count them? One is you actually count the elements in this set and you count the elements in this set and you see whether these two numbers are same. But suppose you don't want to count, it's too big. Suppose this room is very big. I don't want to count number of chairs, number of students. I just will have a cursory view. I will see if there is any empty chair. No empty chair. Yeah, all chairs are filled. But are there two or more students sitting in one chair? No, I don't see that also. Which means the number of chairs and the number of students are fine. Okay, so I don't need more chairs and I don't need to remove any chairs. I don't know the count. I don't know the exact number. But still, I have come to a conclusion that number of students and number of chairs are same in number. This is a logical conclusion. All this is happening because you have some rules like if in each chair there is exactly one entity, then there are as many entities as there are chairs. Suppose this is a rule in my system. Then if that is the case in reality, then I can conclude that in reality, in this room, there are as many students as there are chairs. The rule is coming from the formal system and it is being applied to reality. You see, when you are doing logic in programming also, you are doing logic, right? If x is greater than y and y is greater than z, then you conclude that x is greater than z. Okay, this you are able to conclude because there is a meta rule. I mean, there is a rule of, there is a transitivity property, right? Greater than is a transitivity relation. So that relation you can apply on any pair of numbers. The actual numbers which you take is your reality. But the rule, which is a general rule, is a formal system rule. Okay? You'll understand later when we look at more examples, you'll understand. So don't worry. Any other doubts? Okay. So next feature is, okay, just a minute. So here I need to add one more thing. Related to the formal system F are derivable within F, then F is said to be complete. See, another way of understanding formal system or formal logic is these are the rules of thought. How do we think? Can we formalize the way we think? If we try to formalize the way we think, probably this is how it looks. Okay? There is reality out there, but then this reality is translated into thoughts, into perception, into reasoning. So how do we reason? If we give a language for our reasoning, then it will look something like this. So this is the language of reasoning. Okay, that is the thing. So usually we reason about reality. We may also choose not to reason about reality. We may reason about something completely imaginative. That is why a formal system may be related with reality, or may be related, may be not related with any reality. It can be completely about some imaginary situation. Okay, in that sense, both can be separated or it's up to us. A story is like a reality. I can try to come up with a formal system related to some story. If be it Sherlock Holmes or be it, some fantasy story, it can be anything. Within that story, I can speak of if this happens, then this, then how can this happen? There is logic. We say that no. How are we able to say that? Because formally, there is, it's not real. We know that, but when we watch a movie or when we read it, this is completely illegal. This is not simple. How can this happen? Right? So how are we able to do this? It's not real, but it is. So logic is applicable to either existing reality or imaginary reality. It's rules of thought. Think about actual reality or imaginary reality. So these rules are reality. So again, now let's take some four statements, mostly similar to the previous case. So say area of a circle is pi r square, perimeter of a circle is 2 pi r, and area of a triangle is half bh, and area of a rectangle is length into breadth. Now imagine this is my universe. In the sense, only these statements are true in my universe. That's all. Small universe. I don't have any more statements. Fine. Now, so if you think, these are true in universe U. Okay. Now, assuming these are all the true statements, in my universe U, if they can be derived, in formal system F, then F is said to be complete. Okay. So suppose these four statements are derivable in F, then F is said to be complete. And is it also sound? All these statements, these are the derivable statements, and they are true in the universe U. So Yes, it is not deriving any false statement. Okay, so F is both complete and sound. Now suppose I take some other statement like area of a circle is pi r cube. Now we know that in our universe, that is universe of mathematics, this is a false statement. Okay, if this statement is also derivable in F, then is F complete? It is still complete because all the true statements are derivable. Any more statements you want to derive, it doesn't matter. You should not miss a statement. You should have all true statements, which is happening. You can derive additional statements. It does not matter. So F is complete. But is it sound? No, because it is deriving some statement which is false. All the derivable statements, they should be true. If there is at least one false statement which is derived, then the system is not sound. Okay, so it is unsound. Okay, so now coming to set notation. So if you have a set of true statements, now that set should be a subset of all the derivable statements. Okay, so the true statement set is either a subset or equal to the derivable statement set. Then it is said to be complete. Where this is again same as the previous thing, so I'll just copy. Okay, so here the point is there are some true statements in this universe related to this universe, and if all of them are derivable in F, then F is said to be complete. If it is leaving out some true statements, then F is incomplete. Okay, so a simple way to understand, to think about soundness and completeness is, if you are asked about soundness, you should think from the direction of the formal system. In the formal system, what all statements are derivable? Now, among these derivable statements, is there at least one false statement about reality? If there is one, then the system is not sound. If there is no false statement, then the system is sound. It can be incomplete because it's not capturing all the truths about reality, but whatever it is capturing, it is true. So it is sound. For completeness, you think from the other direction, reality. For completeness, in reality, what all are the true statements? Now, are all these true statements derivable in F? If yes, F is complete. If some statements are missing, then F is not complete. It may be unsound because it may derive for some false statements also, but as long as it captures all the true statements, it is complete. Okay, so it may capture false statements also, that doesn't matter. It should not miss any true statement. That's it. Okay, so both are slightly different. So let's look at example, you will understand this better. So imagine I have some universe U in which there are some true statements like Socrates is mortal, rose is red, and clouds give rain. Some three statements. Okay, let's just take these three. Now let's also take two false statements. That is Socrates is immortal, and maybe pigs can fly. These two are false statements in this universe. Okay, so now we can think of different formal systems which map, which try to model this reality. So I can think of so in F1, say the following statements are derivable. Say only 1 and 2 are derivable in F1. Okay, and maybe in F2, 1, 2, 3 are derivable, and maybe in F3, 1, 2, 3, 4 are derivable, and in some other formal system F4, 1, 4, and 5 are derivable. Okay. So these are the set of derivable statements in each formal system. They can be different formal systems trying to model the same reality. All right. So now, is F1 sound? Yes, because all the statements, like I said, for soundness, you start thinking from the formal system side. What all statements are derivable in the formal system? 1 and 2. Is there even one false statement in this? No. So this is a sound system. Okay. So we can say this sound. Is it complete? No. Now you think from the reality side. What all statements are true in reality? Those three statements. Are all these statements captured in F1? No. One true statement is left out. So F1 is incomplete. Okay. Is F2 sound? Yes. All the statements which are derivable here are only true statements. No false statement is there. So this is sound. Is it complete? Yes. Yes. All the true statements are derivable. So it is also complete. Is F3 sound?
No.
No, because all the statements which are derivable here, there is one false statement. 4 is a false statement. That is also derivable. So the system is not sound. So this is unsound. Is it complete?
Yes.
Yes, because all the true statements are derivable. You can have additional statements, but no true statement is left out. So it is complete. Is F4 sound? No, because all the derivable statements here, there is only one true statement. 2 are false statements. Even if there is one false statement, it is not sound. So this is unsound. Is it complete?
No.
No, because all the true statements are not captured, are not derivable here. Only one true statement is derivable. So this is incomplete. Clear now? Difference between soundness and completeness? You may need to again spend some time on this example. You will understand. This example will capture all the aspects which I explained. Okay. So, like we saw, let me just copy. So, if derivable is a subset of true, it is one thing, and if true is a subset of derivable, it is another thing. So, if derivable is a subset of true set, so is it sound?
Yes.
If all the derivable statements are true statements, is it sound?
Yes.
Yeah, so it is sound. Is it complete? No. Because there are some true statements which are left out, which are not in derivable set. Okay. Similarly, if all the true statements are subset of derivable set, is it sound? No. So it is unsound. Because outside true set, which is false statements, those are also derivable, which means it is not a sound system. And is it complete?
Yes.
Yes, because all the true statements are captured, are derivable. Now, what should be the case for a system to be both sound and complete?
The subsets of each other.
Yes. So, both the sets should be equal. So, if derivable set is equal to true set, then the system is said to be both sound and complete. Okay. Now, what about the system which is neither sound nor complete? How do you represent it in? Intersection of the sets is null. Okay. That's all.
So they're not subsets, but they intersect and maybe quite a lot, but not everything.
Yeah, so two possibilities are there. Either they partially overlap or they don't overlap at all. Okay. If they are equal or if one is the complete subset of the other, then one of these three cases will happen. But if they only partially overlap or if they don't overlap at all, then the system is neither sound nor complete. Okay. So I have the set of derivable statements. And the set of true statements. So they partially overlap. Okay. Or they are mutually exclusive of each other. Okay. So either this case or this case, it means the system is both unsound and incomplete. Okay. Okay. The next feature is consistency. A formal system F is said to be consistent if for no statement P derivable in F, not P is not derivable. In other words, if both P and not P are derivable in F, then F is said to be inconsistent. So let's take the previous example. Let me try to copy this.
So then F2 is done.
F2, yes, F2 is consistent. F1 is also consistent. F4 is also consistent. F3 is not consistent. Sorry, F4 is also inconsistent. Yeah. So let me, what do I say? Let me reduce this size and try to give one more. Okay, so is this system sound? No, because there is a false statement. Is it complete?
Yes.
Yes, all true statements are there. Is it consistent?
Yes.
Okay, what is the fifth statement? Pigs can fly. Is it the fifth statement? Is it the opposite of any of the other three statements? No. Okay, so this system is also consistent. Whereas if you take this one, 1, 2, 3, 4, here 4, Socrates is immortal, is opposite of the first statement, Socrates is mortal. Okay, so these two are contradicting each other. Socrates is mortal and Socrates is immortal. They are contradicting each other. So the system is inconsistent. Okay, and first two statements, there is no contradiction, so that is consistent. Next, first three statements also there is no contradiction, they are not contradicting each other, so that is also consistent. And 1, 4 and 5, in this 1 and 4 contradict each other, so this is inconsistent. So hope now you understand. It's not about truth and falsity. You can have a true statement and a false statement, but still the system can be consistent because true statement and false statement may not be related to each other. Okay. Two statements are related to each other in a conflicting way. System is said to they should contradict each other. Okay.
So if we have a common system with both,
consistent. So if we have a formal system with only 4 and 5, then also it is consistent. Is it sound? No, because derived. Is it complete? No, because no true statement is there. Fine. Okay. So the point is, among all the statements, I mean, each of the features are completely independent of each other. There is one more feature, decidability. I'll come to that in next lecture. Among these three features, sound, completeness, and consistency has its own use. Like soundness tells me that the system is reliable. Okay, whatever output the system is giving me, I know it is true. Yeah, silence please. 2 minutes. Silence. Whatever this system is giving me, I can rely on this output because I know it is true. It may be incomplete, but whatever it is giving me, it is true. Okay, the system is complete. There, it is like okay, it is there is nothing left out by this system. So there can be nothing outside of this system. Whatever is there can be found in the system. Okay. Something wrong may also be found, but whatever is there that is found in the system. Okay. It cannot be practically that useful alone. It may not be useful because you have the system complete, but still you have state, and it is not used. Consistency, it's not able to do the falsity. I can take a false stance and still I can be consistent. Okay. What is like an example? Suppose a bad person, but I see now these both are each other, bad person, but still I can silence. Convert this to a consistent system by okay. Although that belief may be false, the belief is acting good may be false, may be but I may be holding false beliefs. Bad is false. My belief that he is acting good is false. But these two beliefs are at least consistent. I believe that he is bad, and also hold a belief that he is doing good things. Contradicting others. I should change one of them. Okay, so consistency has to do with no contradiction. No contradiction. Maybe. Yeah. No. If a system is inconsistent, it needs not be because suppose I have he asked only 4 and 5. It will not. Not both will need to be there, which means it. Good question. Okay, from next class, I'll take attendance in Juno, so please ensure that you all have Juno accounts. Okay.